So I'm Renaud Eustache, working with the Luxembourg Institute of Science and Technology, and I would like first maybe to thank my co-authors that also work on the Discascade project, Patrick Majen, Peter-Jan van Leuven, Nancy Nichols, Marco Chini, Ramona Pelic, and Carol Delaine. And the talk is about the joint assimilation of satellite soil moisture and flood extent maps for improving the calibration of a conceptual hydrological model. So, and we carried out a proof of concept study based on the synthetic twin experiment. So for the context, everybody agrees on the fact that floods represent one of the most important natural hazards in the world. And one powerful tool, or let's say two powerful tools for flood management and prediction are hydrological modeling, but also hydraulic modeling. The main issue with hydraulic modeling is the computational time that is often rather high to be applied at large scale. So we focus today on hydrological modeling. And one challenge that has to be tackled when using such model at large scale and in many places around the world is the need for observation, especially to set up, calibrate, and evaluate these kind of models. The main issues are that traditional observation are punctual, so field observation, for example. So there is a problem of representativeness when you want to use it for evaluating or calibrating distributed models, especially distributed models. These observations are also scarcely distributed, and unfortunately, observation networks tends to be further reduced. And one last point is that ground observations are not always reliable during flood events because you can even sometimes not collect them due to the danger. So there is the need for new observation to feed this model and to better constrain the hydrological models. And we see two candidates as example that are satellite SAR flood images and satellite derived soil moisture products. One of the main strengths of SAR sensors is that they can acquire good, accurate images day and night and with almost all weather condition. And of course, they offer a synoptic view over a large area. So you can see in this graph some examples of acquisition of SAR images for a given large basin, I think in Africa, and you see each yellow dot shows the acquisition of flood images. And then this, I think, highlights the fact that we have now many images and we have a large data set that can be leveraged for hydrological modeling. So in this study, we assimilate two kinds of information, as I already mentioned. The first one is flood extent map, derived from Sentinel-1 data, so SAR satellite. The revisit time of the satellite is more or less 2-3 days over Europe and 6 to 12 days globally, so rather high revisit time. And we also aim to use soil moisture maps, for example, from SMOS data, so one image every 3 days globally. So the main research question is to evaluate if these two Earth observation data sets are sufficient and can be used to calibrate a distributed conceptual hydrological model, so without using ground truth data, because when you want to map or to predict flood hazard, what is usually done is to calibrate first the hydrological model based on ground data. And if you don't have this ground data for some area, as we don't have this data for many places around the world, the idea here is to compensate this lack of data by using the Earth observation data only. Let's quickly explain a bit how the conceptual hydrological model works. It's rather standard. So it's a bucket model with the different reservoirs that exchange water. So the main forcing of this model is the precipitation that is taken from AR5 in this study. So there are two upper root zone soil layers. So the first centimeter of the soil, so a few centimeters until meter. And you have soil moisture that is represented by the filling, the level of filling of these two reservoirs. For the upper root zone soil layer, you have potential evapotranspiration that is simulated using the Penman-Montate equation. And so this provides soil moisture for the topsoil layers. And then you have there are other reservoirs that assimilate runoff below the ground, so groundwater and soil runoffs, and also surface runoff. So there is a surface reservoir that enables to predict surface runoff, but also flood extent. I will come back to this. So this model is uses ERA 5 as atmospheric forcings and is distributed in space. So meaning that the structure that I just previously shown is repeated over each cell of the model. So in this study, the cell size is aligned with the one of ERA 5 grid. So then each cell flows into others following the hydrological network, and then we focus on a specific downstream cell that is used to predict flooded areas. How does this work? So we have a reservoir that is dedicated to surface storage, surface water storage, and this volume of water that is stored into this reservoir is distributed over the digital elevation model in order to predict flood extent and flooded area. For the assimilation design, the idea is to use satellite soil moisture data in order to calibrate the parameters of the model more related to the upper soil layers, and then at the same time flood extent in order to calibrate the other parameters of the model. So this is more or less a summary of this design. So we use soil moisture observation to calibrate the parameter of these two reservoirs, and then flood extent observation to calibrate the rest of the model parameters. To carry out this calibration and the retrieval of optimal parameter set, we make use of a particle filter, namely the particle filter with tempering. So as usual, in a particle filter, this is based on the bias theorem, where you estimate for each. So you first generate a first guess of the parameters, of course, and then based on the bias theorem and the observation. So this is the likelihood here, the probability of the observation knowing the parameter sets, and then you estimate for each particle its probability with respect to the observation. Since we have a lot of data we want to assimilate, so because we assimilate time series, there is a high risk of degeneracy, meaning that at each iteration step only a few particles remain. So what we do is that we use a tempered particle filter, and we actually factorize the likelihood accordingly in order to start from a rather large parameter distribution with the idea to converge to the correct solution with this factorization using power coefficients starting from a low value, and then to fulfill the particle filter and to end to the factorization. Of course, this coefficient needs to go to a value of 1. So how does it work in practice? We make a first guess with 32 random parameter sets. We run the model, we assimilate the data, and then we get particle weight using the tempering factor. And the tempering value, tempering factor value, is optimized so that we get, after the assimilation, an effectiveness of the ensemble size equal to half of the ensemble size, so 16 in this case. Then we resample these particles and we mutate them using a random walk metropolis hasting algorithm in order to get back some differences between the particles and some variety. And this is done iteratively with different values of phi optimized each time in order to get to phi is equal to 1 and then to approach the optimal solution. So for the synthetic twin experiments, as usual, we first generate the truth. So we make a forward run of the model using a priori parameter sets over 9 years. We generate, based on that, soil moisture and flood extent time series. You can see here an example for a given cell. And then we perturbate the observation. We assume that we have one observation every 3 days for soil moisture, and we perturbate them using a Gaussian noise. We did the same for the flooded area. So here is the time series that is generated from the model, from the truth run. And we perturbate them and assume that we have observation every 3 days. So these red dots represent the data set that is assimilated later on to the model, so the perturbed observation. What we also get from the truth forward run of the model is the discharge time series there that is used as a further control of the model and the assimilation. So as a first experiment, we assimilate jointly soil moisture and flooded area. So here is the different iteration of the tempered particle filter. So with different tempering factors going to 1. So we see that we need a bit more than 100 iteration of this filter to get to the solution. And the RMSE, so the root mean squared error, while comparing the synthetic truth and the calibrated, so the analysis after the assimilation is less than 1% of soil moisture. Same results when we compare the model results after the analysis and the truth in terms of flooded area. So we see a rather small, so each cell corresponds to, I think, 25 by 25 kilometers. So then you see that the RMSE in terms of flooded area is also rather small after the assimilation and the optimization of the model. And the further control based on the Nash-Set cliff efficiency of the discharge, so the surface runoff within the river. We see also that we reach high performance. So the Nash-Set cliff efficiency is a goodness of fit measurements. So the closest to 1 it is, the better the fit between the observation and the model results. So this holds promises for the calibration of such a model using Earth observation derived data. What we did as well is an experiment, while this time assimilating only flooded area, so without soil moisture assimilation. In this case, we see that the model is also the calibration and the assimilation also enable a convergence with a solution with rather low error. Of course, how to say the number of iteration is a bit different because the experiment is different, and we see as well that the runoff is correctly simulated by the analysis. So here are a comparison of the results. So the time series we see flooded areas with the two experiments, assimilating jointly soil moisture and flooded areas, or assimilating flooded areas only. So we see that the results are rather encouraging in both cases, and it seems with these preliminary results that the results yields by the joint assimilation are a bit better, but this needs further investigation to be confirmed. So to conclude, we carried out here a synthetic experiment using a tempered particle filter for the joint assimilation of satellite flooded areas and soil moisture observation. The results are really promising, as the calibrated model is predicting surface runoff accurately, both during the calibration and the validation period. So that's probably what I forgot to mention here, is that this results were obtained for another period, so a period where no assimilation was carried out. Then this opens the floor and holds promises for application at large scale, and especially over poorly gauged data for flood modeling and flood prediction. And as a next step, we see at the moment a further investigation of the added value of soil moisture data, and also, of course, to carry out further experiments, including real test experiments. So I would like to thank you all for your attention and acknowledge the National Research Fund of Luxembourg for funding this project, and also their project in the UK for enabling the collaboration with Nancy Nichols and Peter Jan van Leuven. Thank you very much. I'm happy to answer any question.
Thank you very much, Renaud. We get one question from Javier Amezcua. So he's asking, I did not get the reason for the mutation part of the algorithm after the resampling.
After the resampling, you have many replicates. So the idea is to have in the next iteration more diversity into the ensemble, not to run many times the same same particles without any gain, and not to reach after a few iterations a point where we only have one particle left. So the idea of this mutation is also to regain diversity into the ensemble and to combat the degeneracy issue that is one of the main drawback of the particle filters.
Thank you. And it seems that Peter Jan is writing additional answer.
We have to have a look at it.
Maybe, yeah, you can look at it later. Okay, and I assume that Peter Jan can speak here, no? If you'd like to say something, maybe Peter Jan can turn on the microphone.
Okay, I can, yeah. So,
hello.
Can you hear me? Yeah.
Yes, perfectly.
Nice to see you.
Nice, yes. To see you.
Anyway, no. So the only thing I want to say, so Javier, the thing is that during the tempering, and so then we have to do after every tempering step, then we have to do the mutation, and the reason is that during the tempering we don't do model integrations, and we change we weight the particles, we resample them, and then we have the identical copies, and then we do the mutation, and then we as Renaud mentioned, so then we slowly get to the proper likelihood. Hope that helps.
Thank you very much.
Okay, thank you. So I have a very quick question. So you showed very promising results, but I wonder where you had the most difficult situation while you did this research.
But if I correctly get the question, I will try to answer. But the point is that I think there is we have difficulties to get ground data that could be, of course, the most powerful information to calibrate the model. And then we have now more and more, especially with the Copernicus satellites, so like Sentinel, we have a wealth of data that can be used. So the challenge here, I think, is to show that untraditional data. So you never think about using flood extent to calibrate a hydraulic model, especially time series now. So the main difficulties is to first make the model capable of predicting such information. So to have, because this is not a state variable of any hydrological model. So this is the first challenge. And the other challenge is that you only have observation every 3 days, while let's say the dynamic of flood events is often shorter. So you don't observe all flood events first, and sometimes you have an information that is either before the peak, after the peak, and then let's say that the sampling of the observation is not ideal. So that's also the second main challenge. to try to calibrate a model with, but that's a bit usual in in a simulation. But that's let's say down where the sampling is not enough compared to the frequency of the phenomenon you observed, like flood events, for example.
Okay, thank you very much. That sounds like yeah, common problem in satellite observations. Yeah, thank you very much. There are more discussions in this document, so you may take a look at the document so that Javier and Peter Yan continues the discussions.
Okay, I will
Thank you
do so.
Bruno.
Thank you very much.